Okay, so in this class we will continue what we left off here, yes, in the previous lecture, and we will discuss the conformal algebra. That we'll find the generators, and from the generators we'll find the conformal algebra, and then we'll look at a particular way to understand this conformal transformations that is called the light formalism, and maybe we will have time to discuss or start discussing correlation lengths or correlation functions on CFTs. Okay, so but first let's review what we did last lecture. We discussed what is a conformal field theory, what are conformal transformations. They're just the Poincare transformations, meaning translations and rotations. And for whoever was not here, when I say rotation, I also mean Lorentz transformations. Okay, scalings, which is just zooming in and zooming out in your space-time, all directions simultaneously. And special conformal transformations is a bit more abstract, or it's harder to visualize, but we see that it comes out from the equations. Okay, and what is a conformal field theory then? Is just to implement the symmetries on the Hilbert space, just like we do for standard quantum field theory. Okay, so before we actually started, I discussed one particular consequence of scaling symmetry. That is for interacting theories, we have no notion of particles and of S matrix, because if the theories interact at a length scale, if we scale to plus or minus infinity, time equals plus or minus infinity to find the in and out states like we do in standard quantum field theory, by scaling symmetry, the theory must still be interacting. So you cannot build free asymptotic states. Okay, you do not have free in and out states. So you cannot construct an S matrix. You also have interactions. So the particle concept does not arise for interacting conformal field theories or scaling field theories. Okay. But so what do we compute? We just compute correlation functions. Okay. In the standard quantum field theory, we compute the correlation function, then we apply the LSZ reduction formula to compute the S matrix and compute scattering amplitudes and so on. But this, unless it is a free conformal field theory, we cannot do it. Okay, and but let me just make an observation. You do not have S matrix on conformal field theories, but usually a CFT is not the end of the story. So you can compute S matrix of other theories from correlation function in CFT. One example is the most famous, the ADS CFT correspondence. At one side you have CFT, the other side you have ADS. You can compute the S matrix and ADS from correlation functions on CFT. So if you read the literature, you say, okay, we use S matrix, compute S matrix from the conformal field theory correlator. You're gonna say, well, but so the theory is free. But then you keep reading, you see, okay, the theory interacts. So you might get the impression that S matrix exists in CFT, but he's usually doing computing an S matrix of another theory from the correlation function on the CFT. Not only on ADS CFT corresponds, there might be other examples, but this maybe the most famous. Okay. Just like this. Okay, so just an observation. So then we started discussing what the definition of conformal transformation is just in general, an x-dependent scaling of the metric. You do, you do some transformation to the coordinates. Okay, and the effect of this transformation is just to rescale your metric by in general, position-dependent parameter, which we call the scaling factor. Then this is the definition of conformal transformation. This is for any metric, flat or curved. But here we restrict to the conformally flat metrics, meaning this metric here, the original metric, would be just a Minkowski metric or Euclidean metric. Here, Minkowski or Euclidean. And maybe you want to plead, I might write this delta minimum. Then we looked at the infinitesimal transformations, and meaning this, in general an x-dependent epsilon, meaning the transformation, and then in the end we did some, we massaged the equations, and we found this particular differential equation for the infinitesimal parameter, and we found that the solution is at most quadratic in x, right? Because in the end this implies that the derivative vanishes, so it must be at most quadratic in x. And we can read all the types of transformations we have here. We have the translations, which are included here in the Poincare here. Here the linear, this is the x-independent part, just translations, why you know it's translations. In the x-dependent we have rotations, which is also included in Poincare here, the transformation. And we also have the scalings here. If you remember, we just split this beam in a symmetric part plus unsymmetric part. The unsymmetric corresponds to rotations, angular momentum, generated by angular momentum, and the symmetric part, the proportion to the metric, corresponds to scalings. And we found also another piece, which is can only be the special conformal transformations, which we usually abbreviate to SCT for short. And that's how we know they are there. You may have come across them in studying complex analysis, because they are used a lot in complex analysis and two-dimensional plane. And these are the continuous transformations. Okay, just like in the Poincare group, we have two discrete transformations, meaning parity and time reversal. We also have a particular discrete transformation, discrete conformal transformation, which is of course not included in Poincare transformations, which is the inversion transformation. Meaning we just we computed a vector with the inverse models, so to speak. Each component is inverted model. And it is discrete, and it is useful because it gives a bit more of intuition into what are the SCTs. Because it can be proven, I don't know if any of you did this exercise, but if you take any translation here, say translate by mu, then, I first take the inverse of a point, then I translate by mu, then I take the inverse of all of this. We'll end up with a special conformal transformation, which is a finite expression. I should have written here, my bad. Finite SCT. It had this form. So if I just combine this with translations and compute this, we end up with this. So we can think about the special conformal transformation as translation in the inverse space. We invert everything, translate that, and then invert back. And the erratum that I wrote is here because I wrote the scaling factor corresponding to finite conformal transformations. I guess, I'm not sure, but I guess I told you that last lecture it was this, right? It's actually this, that's a square here. There it is. Okay? That is the erratum. And the way I did not do this computation is because it is just painstaking, long, and actually don't learn anything new from it. Okay? And I guess this concludes the review, comments, and erratum. Are there any questions about this? Leftovers from the last lecture?
No, if you take now the Euclidean metric, just change also the equation for like this differential equation. So it's not above the equation. Yeah, just this one.
Just change
That's
this.
everything that changes.
Yeah. Everything stays the same. And the solution is also this.
Yeah,
but the difference is if you have Euclidean metric, you only have actual rotations, spatial rotations. If you have Minkowski metric, you have the rotations and Lorentz transformations, boosts. That you can think just as rotations in the imaginary time axis. Okay? Any more questions? No? Okay. I guess that's right. Oh no, okay, just let me, before we actually start with that program there, let me tell you one more thing about the inversion transformation that you may read about it in the literature. This is the inversion. This is the definition of the inversion. Okay. You can from this you can. It's just a mess. You can compute if we let's call this x mu y for inverse. Okay, this is the definition. Then we can compute what happens to the differentials. Okay, you just basically just pick this and take the differential. Okay, if you go through the computation, you see that this furnishes this expression. Okay, so the inverse, the differential of the inverse is given by this this factor here times the differential of the actual coordinate before inversion. Okay, and this thing here in square brackets, maybe. This is what we call the I menu. It is the inversion. Tensor. Okay. So you might have been tempted to think that everything would just be applying that definition. Okay. Just take whatever object you have with the indices and just apply that. But that's not true. Okay. The differential transform this under this way because of this definition on the coordinates. Any questions? Okay, so let's start. So the first thing, I guess I'll call this 2.2. That's it. The conformal algebra. Now we'll take this can be seen as a part of the review, but I'll write the infinitesimal versions of all these transformations again. And for the translation, we had the rotations. For the special form transformations, I had is that correct? This last one. It is. This we compute last lecture. I just forgot to put it somewhere in the review. Okay, we'll start from these transformations and compute the generators. So translations, rotations, scales, and SETs. Okay, but actually everyone already knows the generators for translation and rotation, just the usual generators from the Poincaré algebra. Okay, just derivatives or for the translation we have PU, which is this one, right? And in nu we have that I guess it comes with an I instead of a man. This is the orbital angular momentum part, and if the field has a spin, we have I guess that's a factor of half here, and the spin matrices depending on which representation of the Poincaré group those fields will fall into. Okay. For the scalar, this scalar field is 0. There's no spin. For the fermions, we have the commutator of the two direct matrices. For the vector balls, it's just combination of matrices. Okay?
The last term is correct because the last term is.
I might be missing a factor here or not. Maybe it doesn't.
No, because of the contract, you are contracting the indices.
Oh, sorry. Yes. Well, we just write it schematically. Just
something like this.
Yeah, something like this. Anyone remembers? Specific. But the point is there's an orbital part here, and here's the spin. Okay, so I'll just remind you how to compute this one because we compute these two that are new to us. Okay, we just take a field, say phi of x, and we transform it. Say we look at this field at a point x prime. Okay, we can Taylor expand this, and it will be something like there will be the infinitesimal parameter, whatever it is. So I'll just put an Latin A index here. It can be anything. Could be a Greek index. Could be just one parameter, no indices. Okay? Just a generic index. And there is. Let me just put it down here. Okay. Then we recall just at the expansion that we stop at first order in this parameter. Then we just recall the definition of generator. We see that this difference we define it to be minus or plus. Just say it is, what is it? We define the minus I, the parameter, whatever it is, the generator acting on the field. Okay, this is the definition. And then we just look, what we have to do then is just compare this, these two expressions, just plug this into here, and compare this, and choose for these epsilons any of these. So this is the epsilon of translation. This is there was supposed to be okay. This will be the epsilon of rotation. This will be the epsilon of scale, and so on. Okay. Just read it. Right? So whatever that is not x. And so if we choose translations, then our epsilon mu is just a mu, right? So this implies that I just put this guy on the other side, use this definition. That will be a minus I epsilon A GA. And on this side, I just plug mu here. There is no this index for the translation.
Sorry, I think the definition of the transformation, there was the prime and phi, the first one.
It's because I'm taking scalars for simplicity. So the scalars, by definition, would have something like this. In general, any function, right, of the old have an original field. So if you do coordinate transformation, then the new field at a new position x prime will in general be a function of this guy. But for the scalar, we have this definition, just for simplicity. It doesn't matter for actually finding the generators. You could do this game for say 30 indexes. Just be painful. Okay. So we have a mu here, the mu, and phi here. So we just compare this. Okay. And this guy here was just to be right. The index A will just be the. It's a bit mad. It should sorry, should have written it like this. Yeah. And just compare this guy. Once I came wrong, but I guess the definition is this. Because then we have this here. And when we compare, we'll see that the generator is just minus the mu, right? For the translations, which we usually call just the momentum, right? This G mu we call P mu. Okay? So that's the general procedure. Let me just this is what we're going to do for scales and SCTs. Can I erase this for the whiteboard? Any questions? I know it was a bit messy, but we all know what it must be, right? Make sure I don't repeat a disaster there. Okay. Our scalings are epsilon is lambda x mu, right? Just this guy. Okay. So we have. On the left-hand side of the equation, we have something like this. I guess I missed something here too. In the right-hand side, we have. I'll fix that those indices in a minute. In the right-hand side, we have this, or epsilon, whatever it is, derivative field. So epsilon.
So you assume
Derivative.
a scalar field.
Sorry?
So you're assuming a scalar field.
Yeah. Because I'm only interested in finding the generators. So it's just for simplicity. Okay? Okay, if I won't do this, but because if I was trying to find the generators for a scalar field, we'll just find this part, right? If I try to find the generators of rotations for any other field, then I have to find out this part, right? It's just written in terms of the Lagrange and from Lagrange and so on. Okay? So fix this. Okay. Hold on a second. Sorry to erase this part again, but it is. We can write this as actually. There is no factor here. Okay, so sorry about that. If we go back here, we have we just take the variation of our coordinate with respect to the parameter of our level transformation we're doing. Okay, then we just pick out whatever is the actual parameter. Meaning, for the translation it is a mu. For the scale it will be just a lambda, right? I'll just take this variation. I'll just cut this and get lambda. Okay. Sorry. The inverse. I'll just cut lambda and stay with x mu. Okay. And then I just put lambda back here. There's the definition. This is in any quantum field theory book. You can see it on differentiation. I guess chapter 2 is on the references. Vai pay FS, might be a bit of overkill. But here we get the idea. So if you do everything correct, you find this. So just forget about lambda, and then the generator of scalings will be just minus I x mu mu. And forget about the filter. Okay, it should be feel like here. Okay, so we can just read the generator, and this generator we usually call it D. Okay, for dilatations. Okay, so the generators of dilatations or scalings, as I prefer to call them, is just that expression. Okay. Okay, so I'll ask again because that was pretty messy. Any questions about that and this particularly? No? Okay. So for the SETs, we just do the same thing. So let's do a step-by-step design. That factor that appears in the definition here, we read this guy will actually be the what we call B. Just put a do here. Okay, because B is a parameter. You can see it here, or you can see here. It's the parameter of the special Conformal transformation. So we just take the variation from that infinitesimal form that's SET there, and what you get is 2 times for the first bit, 2 minus x squared. Okay, where here our x1a is just okay. Remember that the a was just like a joker index. Okay, it will be whatever it needs to be. Okay, for the scaling it's just a scalar. For the scaling we will just okay, just erase this. There's that. And then we just do this game again in the blue part there, and we find the generator, which we call usually k nu. And let's do it step by step. We have on the left hand side I b nu. So to match the indices, it must be a vector generator. And on the left hand side we have just the parameters and this variation. The mu of the field. Okay? So, okay, we can forget about the field. It's everywhere. We can forget about the mu's everywhere, and then we just put this item on the other side, and this is what we usually call the special K-mu here. Is the special form transformation generator. This here contracts this one, so we'll just write x dot around minus x squared. Okay, so this is these are the two new generators for conformal transformations. The scaling, which is called D, and the K corresponding to special conformal transformations. Any question about that? No? Okay.
That came from?
What?
From the SCT.
This
verse, yes.
This here? Okay.
Just very
That's because I missed this factor before. When I originally wrote this, I missed this factor. Okay?
Can
It's
I
kind
also,
of the finish.
I'm a little bit confused because you call the last term a derivative with respect to nu, but you did the contraction with the delta, quantitative delta. So
This?
yeah, just because I'm confused with this kind of notation, shouldn't it be contraction with the eta? The delta?
No, because in Minkowski, if you have this, the Minkowski metric is, say in this convention, it's just this. Okay? I'm going to say in 4 dimensions.
Yes.
Okay? If we raise one index,
Yeah.
everything becomes Euclidean. Okay, say if we just, let's just raise it. So we contract, we want to end up with that, so that's the index, I have to match. Let's write this, like this, okay? I'm contracting the mu index, okay? So I will end up with something like this, okay?
Okay.
But if you do the matrix multiplication, you see that's just
Okay.
one.
Okay.
So we call it delta.
Okay.
Any more questions?
Yeah,
About this?
Yeah, this term, the second term is above equation. Yeah, this term where you're pointing has a free index nu downwards, right?
Nu.
And the other term has a free index mu upwards.
Let's this again. No. What are you saying?
No,
Okay.
the free index.
Everything is contracted. Okay? Because it was contracted, this guy that just erased. Because I was trying to read the generator.
Okay.
Okay?
No, okay.
Okay, maybe I should have just
No.
crossed the. Okay. Any more questions? No? Okay. So, okay, what we should do now is just take translation generators, and for our purpose we can forget about the speed part. Take the rotation generators and these two new generators, the scaling and the special conformal generators, and just start commuting them and find the algebra. Okay, so this is boring, I won't do this here, I'll just tell you the answer, what is the conformal algebra, okay? You can do this later if you want. It's just a long exercise that. So. So you see why just don't commute everything here. Yeah.
The second commutator is 0, right? Because you repeat everything again with a minus sign.
No, I'm permitting the indexes. Or this is
No,
show.
you-
Okay, no, okay, this one.
And the other one as well.
Yeah,
Is it repeat?
Thank you. Okay, I just take this sum from this here, then I permute this. Okay. Then I take. Okay, I should have.
Sigma with solve.
Should be new here. It is. Thank you. Did I get anything else wrong here? I guess not. Like 30 seconds to take notes on this. Can I erase this part? These two buttons. comments on this? No. Okay. Okay. First of all, I could just put this commutator here with these others, but I just put it here on top because you can clearly see that these three first commutators, just as it should be that point commit algebra. Okay, just like translations and rotations. Okay, and they close into each other. Okay, so it's just the Poincaré algebra as it should be. Okay, so here is standard quantitative theory. Now notice also there is another subgroup here, which is the remarks. Oh, the first would be just we get the Poincaré subgroup, subalgebra. But we also get we also have what we call the scaling subalgebra. Meaning that if you just take translations, rotations, and dilatations or scalings, we see that they close into each other. Okay, this is Poincaré. Scalings commute with the rotations, and scaling with the translation gives a translation. Okay, so they close into each other. So we have another subalgebra and another subgroup, which is the scaling, or just scaling group if you want. So that is the reason. Technically, this is the reason why scaling invariance does not necessarily imply conformal invariance, meaning invariance under the Campbell transformations also. Okay? If we know we have conformal invariance, the full conformal invariance, then we are sure that scalings are also a symmetry. Okay? But the converse is not true. So scalings invariance does not imply conformal invariance. But the converse is true. Okay. Just goes one way. So typically what we need is scaling plus some new assumptions here to get in order for this left-hand side to imply conformal invariance. Okay, these assumptions are general things like unitarity, discrete spectrum, and so on. We may discuss this in another lecture, more specifically. Okay, but this is the reason that scaling symmetry alone does not inherently imply the full conformal invariance. Okay, this is the first remark. Second remark.
Just a question. As you told, scaling the sub-algebra of the conformal algebra, yes?
Yeah.
Another point that by assumption something we restrict our general algebra, theory.
No, these new assumptions are something on the field theory itself, like are things like unitarity, Lorentz invariance, that your scaling symmetry is not spontaneously broken. Okay, assumptions like that. It's pretty general. It's nothing too related to a specific, but they are new assumptions.
Okay, by putting assumption, generally you restrict your theory. So scaling assumption must be a sub-algebra.
Yeah.
And
no, but won't be new. They are not like assumptions on the algebra itself. Okay.
But conformal is great.
Yeah, these assumptions are, I think, physical assumptions like
are more like physical assumptions. They are not assumptions on the algebra.
It's like positivity of the energy spectrum or unitarity or something like this.
Yeah, I mean, at phase transitions you have scaling variance. So do you also have conformal invariance?
Oh, it depends.
So,
I mean, I don't know much about it.
yeah,
you-
there are examples where you have scaling variance but not the conformal invariance.
Yeah, there are
Most
examples.
But
There are examples.
For
Okay, from the top of my head, the only example I can recall is the theory of elasticity,
okay.
because I guess it's not unitary. So you have scaling variance, but you do not disprove that you do not have conformal variance. In the case of phase transitions, critical phenomena, there might be, I don't know. But in principle, if you find a scaling invariant phenomenon, you should be careful before you saying that it is also conformal invariant. The Ising model is conformal invariant, fully conformal invariant. You notice the scaling variance, but I guess originally it was Polyakov who concluded the Ising model is conformal invariant, because he already knew the formal correlators, the correlation functions, so we should compute for ACFT, and then he compared with the correlators of the Ising model, say, okay, it's not the same form, so it must be conformal invariant. Okay, the Ising model criticality, of course. Okay, but you should, in general, should be careful supposing that scaling implies conformal. The majority of examples of interest, of physical examples, in general, it will be true that scaling does imply conformal, but the hidden assumptions will be these more physical assumptions like unitarity, scaling symmetries are not spontaneously broken, Lorentz invariance, and so on. Okay? Maybe we'll talk about this in another lecture, maybe next lecture, or the other one after, because we'll have to discuss the energy momentum tensor. You do all this analysis by studying energy momentum tensor field theory. You just see what the constraints of your energy momentum tensor from the scalings and from special conformal. Okay? But this will be another lecture. Any more questions? Nope? So the next remark is to notice that there is a ladder algebra. You might be put this like this. What I mean is, look at these three commutations here. Just forget about Zen. Okay? Pretend it's not here. You have, if you just play with this factor of 2 and this I factor, in the end, you can recognize that these three commutators imply a ladder algebra for the scaling generator. Okay? The ladder algebra for D. Okay? P mu will act as a raising operator. While P mu will act as a lowering operator. What are they raising or lowering? Anyone wants to take a guess? They are raising and lowering. What are they raising? Eigenvalues of the scaling of D, right? So what are the eigenvalues of D? Okay, more. We should call delta, and this is just the scaling dimension of the state or field. Okay? In a free theory, it is the scaling dimension is just what put a quick example here. It's just how we know if we have a d-dimensional Lagrangian, scalar Lagrangian, like in the kinetic term, have 1/2 the new field. You can read the mass dimension if you speak about it. Mass dimension. It is just the derivatives have mass dimension 1, have scaling dimension 1, and then in d dimensions this implies, because this must be dimensionless, right? Because in an action sitting in an exponential, okay, we take h bar and c equals 1, all this stuff, and then you realize that in d dimensions your scalar field must have d minus 2, right? Because you have minus d scaling dimension here, then this must be have d scaling dimension, so you have d minus 2 because I have two derivatives over 2 because I have two scalar fields, so have v squared here, dimensionally speaking. So this would be the scaling dimension of the scalar field, okay? In a classical theory or a free quantum theory, okay? All the so it might look a bit. So why are we constructing all this structure for something just as natural as this? Like, you can just. There's a reason. Is what I told you last lecture in the motivation. So it's that for quantum theories, interacting quantum theories, you have the anomalous dimension. Okay, the interactions will just classify and so on. You have to renormalize the wave function. You have the wave function normalization, and this implies that in general, the scaling dimension of your field won't coincide with the classical scaling dimension. Okay, you have an anomalous dimension, and this gets schema as a common. Okay, so that's why you cannot just start an interacting problem. Just say, okay, the scaling dimension of this field is this, so I just can apply all this structure and I know everything. In general, you do not know this guy yet for interacting conformal field. Okay? Or interacting quantum field theory in general. Okay? So just what I mean by scaling dimension. This one. Usually on particle physics it's called mass dimension. Okay, so any question about this? Let me just say that this is the most important remark. Okay? There's one other, but this one is the most important. This is clear. Is this clear? Okay. So I'll continue on this one. This LED structure. So what would be the structure of the states?
I look. So what about the eye? Isn't it like so the eigenvalues of D are purely imaginary, or?
Yeah, we'll come to this. Not in this lecture, in another lecture. But it will imply that the eigenvalues of D are imaginary.
Okay.
So you write it. So you write delta equals I or minus I. I don't remember the delta.
Okay.
Tilde, and this guy will be real, and so on. Okay. But this is related to the fact that the scaling transformations are not bounded. Okay. So it has you have group theory theorems, representation theory theorems that the eigenvalues must be imaginary. If you have unbounded transformations, then the eigenvalues must be imaginary, very imaginary. So, okay. But we'll come to this in another lecture, and we'll try to when we actually start implementing this symmetry on the Hilbert space. Okay. Just studying the conformal transformation, the conformal algebra itself. Okay. When we come to enforce this all these things on the Hilbert space, we come to these questions. Okay, in another lecture. Any other questions? Okay. So what will be the structure of the states on this theory? So I will just classify the states, or organize the states, or label. Let me just label is more common word for this. We just label the states by their scaling dimension. Okay, because we have the letter alpha. It's just a natural thing to do. And also we can also use spin, because you see that okay, so we can measure both at the same time. That's it basically. But if you look a bit closer, you can see that from actually the ladder algebra, the first relation of the ladder algebra says that D and P mu do not commute. P0 is a Hamiltonian. It has to do with energy. Okay? So you see that the scaling transformations do not commute with energy. So if we choose to, in standard quantum field theory, don't have any of this, we just have this bit. So we just say, okay, I'll classify my states by their mass, or their energy, the momentum in general. Energy and 3 momentum. Okay? And we can also, from especially the Hamiltonian here, we can see that one of these commutators vanished, so we can measure the spin. And that's what we do in standard quantum field theory. But here you can see that the scaling dimensions, which we use to label the states, do not commute with the Hamiltonian. So you might be worried about unitarity. Okay, you could have all sorts of things. You could have negative states popping all over, and your theory would be undefined. And why do you do this? So what you must do is NS. Just write it because I cannot find this anywhere without any scheme. And so question, what we do with, what about energy positivity? Anyone to guess an answer to this question? What you must do about it? Nope? No? Just a guess? Okay. The answer is just impose it. Okay? So when we construct CFTs, we will classify states by the scaling dimension and spin, if they have spin, and in order to save unitarity, we just impose that it will be unitary. So this will lead to constraints.
Yeah, but in standard quantum field theory, you also impose it, right? Energy positivity.
Yeah.
You don't get it.
Okay, but it would be much worse.
Okay.
In principle. Okay.
But in quantum field theory,
Yeah,
you also
in standard
impose
quantum field
it.
theory, you usually have to either impose unitarity or at least check it. Okay. But here the problem would be even worse. Okay? Because you're not even labeling your states by energy eigenstates. Okay? Any more questions? No? So when we impose this, we will be taking constraints on the scaling dimensions. On the, let me write this as on the spectrum we'll end up with constraints on the spectrum of the scaling dimensions of your states. Okay?
Which means that it will be only possible to construct CFTs for these certain values of the scale.
Okay, that was actually my next point. If your theory is not unitary, if your CFT is not unitary, it doesn't mean it's useless. You have lots of non-unitary theories that are useful. Take for example Fermi theory. Okay? The four-Fermi interaction, point interaction. It was non-normalizable and it was non-unitary. Nonetheless, it was one of the most useful theories before you actually discovered the electroweak theory. Okay? But if you do want a unitary theory, say you're searching for fundamental theories, a fundamental CFT or so on, so you just impose it, and what you will get constraints on the scaling dimension, on the spectrum scaling dimensions. Okay? And this is another observation, just we'll use this part here. In CFTs, when we talk about the spectrum of CFTs, is just, we mean this guy here, okay? We mean the scaling dimension and the spin, okay? We do not mean the mass, the inertial mass of the states, okay? Simply because you're not quantizing the moment operators, okay? It's just a change of language compared to standard quantum field theory. And usually, the scaling dimension spectrum is discrete. because they are counterexamples, of course, and relevant counterexamples. Okay, but we got that. This S looks like a delta. Okay, is there anything else? Okay, just a picture. So say, just continue it. Don't wanna erase this one. Run out of space. And another thing about that remark still is that, of course, you must have a state with a given scaling dimension, which we call a primary state, which we call a primary state, meaning, by definition, is a state that is annihilated by because in U the special Hall transformations are the lowering operators. Okay, so there must be states that are the lowest state on the spectrum. Okay, and then we can construct that spectrum, the other states, and so on, just by applying the raising operator. Okay. You might just take a mu here, just take a mu, and so on. Okay, this is just schematic. And so if this has scaling dimension delta, this guy will have scaling dimension delta plus 1, this one will have scaling dimension delta plus 2, and so on. Okay? Remember that the question is we usually do not know a priori the value of this scaling dimension. And we cannot just read from the Lagrangian if we have a Lagrangian. Okay? And these guys here are called the descendant states. Or if you want, some people also call them the secondary states. Okay. And let me just give you a warning, anticipating the case in D, that in two-dimensional CFT, there will be language change. In a CFT, there will be another thing that we call primary operators, and we will have additional definitions. Okay, so just be careful if you're reading two-dimensional CFT text or a higher dimensional CFT text, because in this text, primary refer to different things. Okay, just a warning. But secondary states, descendant states are always this. Okay? And finally, you think this is the third remark? No, still the third remark. This lattice structure of the conformal algebra is the reason why CFTs, or say conformal, put it this way, conformal symmetry is much stronger. Okay? Just an internal rule. It's much stronger than scaling symmetry alone. Okay? If you only have, again, the scaling symmetry, then we still have scaling dimensions as a quantum number, but it would lack this ladder structure algebra. Okay? and the theory would be much less constrained by this. So this lattice structure is responsible for the much stronger constraints of CFTs compared to scaling field theories alone. Okay, so that's why I said this long remark is the most important remark. Okay, this is at the heart of CFT. This is at the heart of the power of CFTs. Okay, any questions? Nope. Okay, so we'll move to the last remark. I want to keep this, so it's okay for me to erase this half. Okay, the first remark. Okay, C. So we found the conformal algebra. So what is this algebra? What is the conformal group? So let's count the number of generators. We have translations, right? Plus rotations, plus scalings, plus SCTs. Okay, so in D dimensions, we have D translations, right? It's just a vector. Rotations, you might recall that in D dimensions we have D times D minus 1 over 2 rotations. Okay, just plug D equals 3, D equals 4. Focus yourself on this if you don't remember. Scalings, we just have one, right? It's just a scalar generator. Okay, remember it's just zooming in, zooming out, every direction simultaneously, so it's just one generator. And SCTs is again generated by a vector generator, so we have D special conformal transformations in D dimensions. So, total, if you just sum this, you find 1/2 of D plus 2, D plus 1. Okay? Does anyone recognize this? What algebra could furnish these many generators? No? Sit. Look at it. So, okay, we're sitting at D dimensions. Okay?
D is plus 1.
Almost.
Oh yeah, D plus 1 over 2 is S whole.
Plus 2.
D
plus 2.
times. No, that's
plus 2.
whole.
Plus 2. Okay, if SOD, this is SOD, right? Rotations in D dimensions. This is SOD. So we have this. We have we should have SO D plus 2, right? Because then it's the D plus 2 minus 1. Okay? So it will be rotations in D plus 2 dimensions. But it could actually be many things. It could be, say we start with the mean count. Say we start with, for simplicity, Euclidean. Say we did everything here for an Euclidean D-dimensional space. D-dimensional. Okay. So we could have SOD plus 2, right? But we could also have, say, SOD plus 1, right? Could be time and direction, or it could possibly also be SOD2. Okay, and we could have a similar list for Minkowski spaces. All right, we know that at most we must have D here. We know that at least we have D Euclidean dimension. Okay, because we have a Euclidean dimension space. Okay, for Minkowski Minkowski, just for completeness. For Minkowski, we have could be we start from something like this, then we add 2 dimensions. So we could add 2 dimensions here and end up with this, or you could add 1 dimension here, 1 dimension here, or you could add 2 time dimensions and with something like this. Okay. So all these 3 groups, either for a Euclidean space or Minkowski space, will furnish this many generators. So how do we decide? And the answer is, I don't know. It's probably a mathematician who found this answer, but
You are talking about a group or the algebra?
whatever you
Not
want.
the same. Not the same thing.
Oh yeah, I know it's not the same thing, but okay, because you could have still non-connected. You could put in the discrete components. I'm saying the same because I'm only worried about the continuous component of the algebra. Okay, the component continuously connected to the identity. But for definitely, we could say the algebra. Okay, we're talking about algebra. Okay, it has many generates, and I know that these algebras at least are the most common. I don't know if there is any exceptional groups that furnish something like this. I don't know. Okay. Did I answer your question? I am satisfied with that answer. Okay. Any more questions? Okay. So the answer to this question, how do we decide, was probably found by a mathematician. I don't know, but in the physics literature, as far as I know, it goes back to 0. Oh, of course. Okay. And the answer is that we must add